Hey, hope everyone is doing well. Hope everyone is, uh, got a safe place to be and is settling into what seems like it might be a while. So, what I wanted to do today was to start us in on moving forward with the new material. I'm going to send you instructions next week on how to hand things in. I think I'm going to use the Canvas quizzes and the sort of nitty-gritty details of what's going to happen. But the basic idea is I'm going to, on these videos, I'm going to go over some questions. I'm going to ask you some questions for homework, and then I'm going to ask you some questions to look at for next time. A person should, for next time, should try the questions, all of them. Now I expect that a person will get stuck. A couple of the questions will give somebody trouble. I just didn't understand what to. That's fine. That's fine. That's what we're about. Then I'll come on next time and go over all but a couple and then ask you to hand those ones in, to type them up in LaTeX and hand them in. Again, I anticipate using Canvas quizzes just to do the grading. Makes it easy for folks to see the grading and the comments and all that kind of stuff. Okay, so to start here, we're looking at the, whoops, wrong one. We're looking at the questions here on page 7 in the book. So maybe if you have your book, took it out, open it to page 7, that would be a help. Okay, and I think that we last time when we left, I think we finished with this question here where you're supposed to produce 3 sets. The intersection is empty, and but any pairwise is non-empty. So we're on to the next. Plan to do all of these. Talk about all of these today. Okay, so the first thing is a definition is that for any set A, finite set A, the order is the number of elements, and you notice the order is just a vocabulary word, but you notice that the notation says absolute value. In mathematics in general, anytime you want to say that something is the size, the right way to measure size is it's natural to use absolute values. So for example, if you want to measure how long a vector is, you write absolute value bars, this kind of thing. So how far from the origin is a number, you write absolute value bars. Anytime you want to measure size, and so the size of a set is the number of elements in the set. So just a vocabulary word. But in general, in mathematics, when you read something like this, when you read a definition, or when you read, it's important to be active. It's important to take out a piece of paper and to figure it out. Try to write down a couple of things and see if you can make out, what in this case the definition is about. So I've done that. I've taken out a piece of paper here, and I'm gonna write down a couple of quick examples for order of a set. And maybe, for example, I might write here. How about the set 0, 1, 2. Okay, and if I say order by putting absolute value bars, then I'm looking at 3. Whoops. See, my handwriting is just as bad on video as it is on the board. How about 0, 1, 2, 3, 4, and absolute value bars makes that a total of 1, 2, 3, 4, 5 elements. Okay, so what's important when working your way through mathematics is to try to be active, is to try to be thinking with your pencil all the time. Okay, the example that the next question says that to ask a person to prove that if you have two finite sets A and B, if A is a subset of B, then the number of elements in A is less than or equal to the number of elements in B. The order of A is less than or equal to the order of B. So again, it's important to be active. A person wants to take out a pencil, and probably the wrong thing to do is to say, I'll sit down and prove this right away. Probably the right thing to do is to first put down an example A or B kind of thing, just to get started, just to make sure you understand the question. Okay, fair enough. So I'll use the 2 that I have on the page here. So let's see here, bring my page up again. I'll use the 2 that I have on the page. So I'll say A is 0, 1, 2. Right. And B is 0, 1, 2, 3, 4. So sure enough, A is a subset of B. And when you count, of course, you get 1, 2, 3 elements here, 1, 2, 3, 4, 5 elements here, and so you do the number of elements in A is a subset of, excuse me, is smaller than or equal to the number of elements in B. One advantage of having thought this through with a pencil is that when you go to do the argument in some problems, and this problem is an example, when you go to do the argument in some problems, you immediately get the argument. Because here, for example, you have A0, A1, etc. through AN. And over here, because A is a subset of B, you also have A0 through A1 through AN. And then some more, maybe, B0, etc. through BK. And it's indeed obvious that there are more elements in B than there are in A because every element in A is in B. So that is to say, when a person goes to do the proof falls right out of the example that we just did by hand. So that's another advantage to doing the examples by hand. All right, let's talk about the actual argument then. Here's an argument written up nice so you're not struggling with my handwriting. Since A is finite, we can list its elements, A0 through AN, inside of curly braces. Similarly, B is finite, so we can list its elements, and because A is a subset of B, the elements of A are elements of B, so there they are. The elements of A are inside of B. And then possibly some more. And indeed, that B has more greater than or equal to elements of A than the number of elements of A is perfectly obvious at that point. Okay. So back to the book, and we've just done 19, so now we're thinking about 20. 20 is the definition. For any set A, the power set, see it looks like a scribbly P, a script P. Power set of A is a set of all subsets of A. So power set is a collection, it's a set. And inside that collection, in order to get in that collection, the criteria is you have to be a subset of A. Not an element of A, subset of A, inside that collection. And to be active, I would take out a pencil and start working, but in fact the next exercise asks me to take out a pencil and start working, so I'm going to skip right to the next exercise here. It says to list the elements of each power set, and then there are 4 separate parts. So the next question is asking me to be active, so I'll skip through that part and go straight to the question. So here we go. The first thing is the question asks for the power set of 0, 1. So power set, so script P of 0, 1, 0, 1. Okay, and I'm looking to have a collection, so there's big curly braces, and inside of this collection is going to go every subset of 0, 1. So the first one that occurs to me is to have just a 0. The second one that occurs is to have just a 1. And I hope it occurs to everybody to put the empty set. I hope. Oh, I got to put commas. Sometimes the commas make more of a mess than a help. But there's one that you might miss, the one that you might forget. Don't forget the set 0, 1 itself. It's a subset of itself. That's fair. So 0, 1. Question asks me to count the number of elements at 1, 2, 3, 4. Okay, that was the first. The second thing asks me for the power set of 0, 1, 2. Power set of 0, 1, 2. Okay, again, a collection. Turns out I'm going to need a little extra space for this collection. So off I go. Just a 0. Just a 1. Just a 2. Don't forget the empty set. And now you see I'm running on to the next line. What I've got here, though, is that's the subset that has 0 many elements. These are the subsets that have 1 element each. And so the next line is going to contain the subsets that have 2 elements each. Okay, fine. 0, 1. 0, 2. 1, 2. And now the pattern is perfectly clear. I need to put on the last line, I'm going to put the subsets that have 3 elements. 0, 1, 2. 0, 1, 2. So the subsets that have 0 elements, the subsets that have 1 element, the subsets that have 2 elements, the subsets that, and by writing it in a systematic way, I have some hope that I've actually listed them all, haven't missed any. 4 elements there, 8 elements here. Now, a thing that's interesting about this question that we've talked about in class a number of times is that the question goes on to ask me to next write not the power set of 0, 1, 2, 3, but instead the power set of 0. And we've talked about this in class before. Sometimes the smaller cases are actually a little harder, or at least it's a little harder to understand the pattern in an edge case than it is to understand the pattern in a bigger case. So the pattern in these bigger cases is clearer than the pattern in the smaller cases. It's kind of funny that way. Sometimes easy things are harder. We've seen that a number of times in class. Okay, so the power set of 0 of the set containing only 0 is, let's see, it's going to be a collection. And again, the first thing that occurs is the set containing only 0, and the second thing that occurs is the empty set, and that's it, I think. There are no other subsets. And then finally, the last thing that the question asks for is the power set of the empty set. So really an edge case. It's a collection, all right, but don't make a mistake here. It's got something in it. It's got the empty set in it. Every element of the empty set is an element of the empty set, so that belongs in there. So one of the things you see is that the empty set is in every one of those power sets. That's a pattern. Another pattern that you see is when the set has 0 elements, there's 1. When the set has 1 element, there's 2 in the power set. When the set has 2 elements, there's 4. When the set has 3 elements, there's 8. So there's some kind of power of 2 thing happening here. Again, we've seen this thing before where sometimes something is so easy that it's hard. So another tip for when you're working on the mathematics at home is don't try easy cases first. Try kind of a more generic case, kind of a more middle case, and then go to the edge cases as the second thing you do. And you see that too in programming. I think a person sees that in programming. Okay, next question here is, next question asks something else about power sets, and I'm going to ask you to do this one for homework. I'm going to ask you to type that up in LaTeX and send it in, and again I'm going to send you an email talking about exactly what the details of how I want you to do that is. And likewise too for 23, I'm going to ask folks to write that up in LaTeX and send it in. But I wanted to make a comment before I moved on to the next question. So perfectly possible that a person would have trouble with this question and would say, I just don't know what to do. I'm really stuck on part 4. Okay, perfectly fair. We're doing what we can with this online business. Please don't hesitate to contact me. I'm going to have office hours via Zoom. Those will be, again, I'll include you in a message next week about the exact sort of low-level details of how we're working. I'm going to have office hours in Zoom. That's a great thing to do. Another great thing to do is just simply send me an email. So if you're stuck, if you think there's some small point that once you get unstuck on that, you'll be good. Please don't hesitate to ask. That's exactly the business that that's why I got into this business, was to help people learn mathematics. So I know you won't hesitate on those. We've been very good about it through the semester, and we're going to continue to be good about talking through the issues that arise. I did want to point something out about this question here. You notice the difference here in part 3 and part 4. This says element, this says subset. So remember how you check whether something's an element. It says open curly braces, empty set, close curly braces. You have to look in the power set of A and say, is open curly, empty set, close curly the first thing in that collection? Is open curly, empty set, close curly the second thing in that collection, etc. So that's how you check element. You go through power set of A and see, it is the entire thing I've got, first or second or third or whatever. Now what's the difference with subset? So with subset, you don't look at open curly, empty set, close curly. Instead, with subset, you look at everything between the two curlies. In this case, there's only one. There's an empty set. And take that, in this case, only one thing, and look in power set of A. Is the empty set in there? So don't, pay attention to the difference between 3 and 4. That gives people trouble. You'll see the same thing over here between 5 and 6. And of course, the question got asked exactly because it gives people trouble. That's exactly why it's there, was to raise the issue that folks see there. All right, so I'm going to ask you to do this one here. These two questions, number 22 and 23, I'm going to ask you to type those up for homework. So we're thinking about the last one right now. We're thinking about 24. So 24 says, where A is a finite set, prove that the number of elements in the power set is equal to 2 times the number of elements in the set. And we saw that when we wrote down the examples earlier, not a coincidence, of course, we wrote them down exactly to make this point. The number of elements in the power set is 1. There's 0 elements here. 1 is 2 to the 0. The number of elements in the power set is 2. There's 1 element here. 2 is 2 to the 1. 2 elements takes you to 4 elements. 3 elements takes you to 8 elements. So exactly what we're trying to prove is that the size of the power set is 2 raised to the exponent size of the set, order of the set. Okay, and we're going to prove this by induction. The base case is very straightforward. Here's the base case right here. So base case very straightforward. For the inductive step, though, there's something that a person wants to notice, and I'm going to point it out to you before I go over to the actual argument, just to save ourselves a certain amount of confusion when we get there. So the thing to notice here is that in 0, 1, 2, these sets break into 2 categories. There are subsets. I know there's 8 of them here, but there are some subsets have a 2 in them. Do you mind if I circle? There we go. There we go. There we go. And there we go. Some subsets have a 2. Some sets do not have a 2. Can I look at the subsets that do not have a 2? Empty set, just a 0, just a 1, and 0, 1. And you look up here, and that's exactly, so this is the induction. The induction is, you find the prior case because it's all the things in the collection that do not have the newest number. All the things in the collection that do not have the newest number. So the inductive step is to look at all the things in the collection that do have the newest number, in this case the 2, versus those things that do not. How many things do not? Well, the inductive argument will say that that's 2, in this case 2 to the 2, but in general it'll be 2 to the k. How many things do have a 2? It's the same number. Why is it the same number? Well, because they match. 0, 1 matches 0, 1, 2. This is the same thing, only without a 2. 1 matches 1, 2. It's the same thing, only without a 2. 0, 2 matches 0. It's the same thing, only without a 2. And 2, singleton 2, matches empty set. So the basic argument is to notice that you can split the power set into 2 separate parts. And that'll be the inductive argument. And then and I know my handwriting is a struggle. So let's go to the part that doesn't involve my handwriting. And there we go. Okay. So as it says, we're going to use induction on the number of elements in A, and the base step is the one that we've already talked about, very straightforward. The power set of the empty set is just a set with 1 element, and that element happens to be the empty set. 2 to the 0 equals 1. So we've talked about these issues before, and so that base step, as so often is true, the base step is very straightforward. Then for the inductive step, the skeleton of the inductive step always goes the same way. We assume that the statement is true up to some case. I like to call the case K, just, I don't know, I got in that habit. So we assume that the statement is true for all the cases up to case K, and we consider a set with K plus 1 elements. There we go. I listed the last element because, as we saw with the pencil and paper, I'm going to want that last element. And then, elements of the power set, that is to say subsets of A, fall into one of 2 categories. Either they don't have the latest thing. In my pencil example, it was a 2. So either they do not have the latest thing, or else they do have the latest thing. How many of the elements of the power set do not have the latest thing? Why, it's very straightforward. Those are exactly the number of subsets in the most recent, in the n equals k case. So that's 2 to the k. And then to finish, I have to show that the number of sets that do have the latest thing, that do have a to the k, in pencil it was 2. The number of elements of the power set that do have the latest thing is the same as the number of elements of the power set that don't have the latest thing, and I'm going to show that by arguing that the collection of subsets containing AK has the same number of elements as the collection of subsets that don't contain AK, and I showed why that's true because they match up in a one-to-one way, and then that'll finish the proof because then we have the ones that don't contain AK and the ones that do contain AK, and the algebra just takes you to 2 to the k plus 1. So for that argument, for every subset of A that contains AK, we associate a subset S hat that does not contain AK, namely S hat is simply S with AK taken away. There's one and only one such S hat, and so the two collections have the same number of elements, and so I'm done. Okay, now that argument's a little on the tricky side. We see over the course of the semester, a lot of arguments. There's an array of them. Some of them are more straightforward. Some of them are trickier. And I mean, the fact is that some arguments are a little harder. I don't know if a person says to me something like, "I don't know that I would have thought of this." Okay, fair enough. There's sometimes that and then eventually you get it, and sometimes you don't. But nonetheless, a person can see that the skeleton of the induction argument is right here, and that if you spent a long time on it, if you spent a week walking around going, "Oh, what do I do? What happens if I try this? What happens if I try that?" I think you'd get it eventually. Okay, so fair enough. So back up here to there we go. Back up here to the book. So that's typical of what we're going to try to do. I'm going to go over some on the videos, and I'm going to ask you to do others of them for hand-in on, I'm going to ask them hand-in on Canvas just for the mechanical reasons that I mentioned. For next week, what I'd like you to do, in addition to doing those two examples on page 7, we're going to go on to this section that's called Cartesian product, and we're going to do all of them. So we just did 5, and now we're going to do there's 7 here, so we're averaging 6. And of course, I'm going to at some point in the course of next week, I'm going to ask you to do some of these, type them up in LaTeX, and send them in for homework. Okay, and so again, anticipate coming from me will be an email explaining the mechanics of how a person is going to hand in the problems and all that kind of stuff. And that should be coming Monday or Tuesday. That's how I understand the schedule that we were given. But in the meantime, you could certainly go ahead and have a look at those, and that would give a person a way to move forward. Okay, thanks very much. Sorry that not seeing you all the time. I enjoy the classes, and I'm going to miss them. All right, so again, hope everybody is well, and I'll be sending in an email. Bye-bye.